Well, let's begin here, folks. So, over the weekend, you guys should have done the worksheets 1 and 2 from Chapter 7 before we get started on the next set of topics. Does anybody have any questions from either worksheet 1 or 2? Fraser?
Would you go over 4 and 2?
So here I tell you to use the compound interest model. So it says you deposit $5,000 on January 1st, 1998 into a bank account that pays 5.5 interest compounded weekly. Write an exponential model where A represents the value of the account after T years. So A and T are going to be my independent and dependent variables. So P, I remember, represents the principal or the initial investment, which in this case would be $5,000. R represents the interest rate as a decimal, so that's the 5.5%, which I turn into 0.55 when I divide by 100. N is the number of compounds per year. It says it's compounded weekly, so how many weeks are in a year? 52. It says, what will the account's value be? What will the account's value be on January 1st of 2012? So 2012 from 1998 is 14 years later. So I'm just going to take my model that I wrote in part A and plug 14 in for T. Stop talking, please. $5,000 times 1 plus 0.055 divided by 2 to that. Times 14. So that's $10,794.44. Remember that number right? Okay. So far, so good for you. Okay, and then part CS. After how many years is the account worth $15,000? So this is something I'm going to do all on my calculator. So I'm going to put 15,000 into one of my Y slots, and then my model into the other. And I'll set a window. So X is representing T, which is time. The minimum time is 0, obviously, since time doesn't really become negative. After 14 years, it gets to 10,000. I need to get to 15,000, so I don't know. I'm going to pick like 30 years. I think it'll get there in that time. The minimum value that the account can have is 5,000 since it's in the account value is increasing over time. And the maximum needs to be at least 15,000. I'm going to do 20,000 just because it's a nice round number. And if I hit graph, there's my line for 15,000. here is my curve, and what I'm looking for is this point of intersection. So second trace, intersect command, and because I only have two curves and they're only intersecting one time, I can just hit enter 3 times. And my answer is about 20 years, so 19.99 would be my value for t. Other questions from this? Walter?
Can you go over like how to graph on the first homework? Like, I know how to get like the numbers in the box, but can you just go over that?
Do you have a number in particular you'd like to do?
It doesn't matter. No.
All right. So let's just say let's do number 2 just for the sake of argument. So it says list the values for A, B, H, and K. So those are my values for A, B, H, and K. Are we okay doing that? Okay. It says state whether this is growth or decay. So since A is negative and B is between 0 and 1, that means that this is growth. Says write down the equation for the horizontal asymptote. The horizontal asymptote is always y equals k. So that's just going to be 4. Then it says draw and label an xy axis, make a 5-point table, plot the points, graph the function. So I'll make my xy table. So I'm always going to pick my points the same way. I'm going to do h minus 2, h minus 1, h plus 1, and then h plus 2. Since h is negative 3, that's negative 5, negative 4, negative 3, negative 2, negative 1. And then to get my y coordinates, I'm going to just plug these values back in for the x in my function and evaluate it on my calculator. So I have negative 1 times 0.5 to the negative 5, that's my first x. Negative 5 plus 3, and then plus 0. And I'm just going to kind of continue doing this, except I'm going to go back and just change my negative 3 to a negative 4, and then change it to a negative 3, etc., etc., etc. Then I'll draw my axis and kind of plot my points. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Drawing my horizontal asymptote here at y equals 4. Plot my point points, so negative 5, 0, negative 4, 2, negative 3, 3, negative 2, 3.5, and then negative 1, 375. So it's going to look like this. And then the last piece asks for the domain and range. The domain is all real numbers for every exponential function. And then the range depends on a and k. So since the a is negative, I know this is going from negative infinity up to k.
How do you know if it's growing through k again? Like, what's the influence?
So on the notes on 426, we listed the criteria right here. So if the b is bigger than 1 and the a is positive, it's growth. If the b is bigger than 1 and the a is negative, though, it's the opposite, it would be decay. If the b is between 0 and 1 and a is positive, it's decay. Or if it's the b is between 0 and 1 and it's negative, it's going to be the opposite, it's growth. Any other homework questions? Okay. So, in the previous lesson, in the previous lesson, we had talked about this compound interest formula, right? And this was a little bit new because here, instead of the change happening all at once, one time per year, the annual change is kind of incremented out periodically throughout the year, right? Into these little increments where you get like, oh, I get 1/4 of the change, at these points instead of getting all of the change all at once. What we're going to do is we're going to take this idea and try to extend it into like a biological situation. So imagine we're talking about a population of animals. And let's be talking about the population of humans, right? So how many humans are there on the planet? 7 billion or so. That's a lot, right? So if we're going to be trying to describe how the population of human beings is changing, how often does that population change? Every day? Every second? Maybe even more often than that, right? You got 7 billion people that are either having babies or dying. Population's changing really a whole lot, right? So what would be the biggest value for n we could have, right? It's going to be more than weekly, which was 52, more than daily, which was 365, more than secondly, which we're my theater people that know the number of seconds in a year. That's in a Rent song, I think. No? Okay, fair enough. But it'd be more than that number. What would the n be in that case? If it's happening like at every instant, the biggest value for n we could have is infinity, right? It's the biggest, represents the biggest value that we can have for something. Everybody agree? If something is changing at any instant, if you look at the number of times that changes per year, it's infinitely many, right? So if we set all of these values to be 1, what we're going to be interested in here is finding the value of this when n is infinite. Now, can we just plug infinity in here and evaluate it and get a number? So what can we do? Well, one of the things that we can do is we can plug in some numbers for n and make them bigger and bigger and bigger and kind of see how that's changing. So I'm just going to use some powers of 10. So I have like 10 to the 0, 10 to the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, all the way down to 10 to the 32nd. I don't know, I just made a whole bunch of values. Everybody okay with that? So when n is 1, we get 2. When n is 10, we get 2.59-ish. When n is 3, we get 2.70-ish. When n is 100, we got 2.70. When n is 1,000, we get about 2.71 and change. When it's 10,000, 2.71, and it went up a little bit. When it's 100,000, now we're at 2.718 and change. 2.782 and change when it's a million. When it's 10 million, it's 2.78282. And we can kind of continue doing this until it overflows the calculator, apparently. Excel, that's not right either. So Excel broke at some point here, guys. Hate to tell you.
Basically, are we using Excel for a group?
No, I'm just kind of demonstrating what's going on.
You can use Excel to do what though?
I would not. I would just use my calculator. We'll see why in a second. Why is Zoom dropping every 2 minutes here? Oh. So, what is my result here? Sure. What is the takeaway? Is that this value is about 271828, yada yada yada. Now, notice that each time that when we looked at our Excel, as n got bigger, this number changed a little bit, right? Would you agree? Now, as n continues to get bigger, it's going to continue to change, but it's never going to get too big, right? It's going to stay around this 271 number, but it'll pick up a little bit more at every decimal point. So is this number ever going to end? No. Like it has an infinite decimal to it. Is there going to be like some repeating pattern to this decimal? Does it look like there's a pattern so far?
It just looks the same. It's like the same number.
What I'm talking about is inside of one of these. Like, is there a pattern going on in the decimal part? Like 1/3 is 0.333333. Like there's a pattern to it, right? Do we see a pattern in this decimal? So what do we call those numbers that go on forever, have no pattern? Those are irrational numbers. And we're going to give this particular irrational number a name. We're going to call it E. Sometimes this number E is called the natural base, or sometimes it's called Eulers number. We name that number E to honor the mathematician Leonard Euler, as he was the one that kind of developed the mathematics that we kind of illustrated there. And he's one of the faces on the Math Hall of Fame there in the back. He's got to be on there somewhere. Yeah, on the far right, second on the top.
Which Pythagorean theorem?
Pythagoras didn't actually invent that. There's the cult of Pythagoras, and they're, as a group, are responsible for the Pythagorean theorem,
I seen like a.
but isn't actually credited to Pythagoras.
I've seen a crazy like fun fact video about that guy. And it was like so much crazy stuff he did other than that. I couldn't actually tell you because I forgot it. But when I first heard it, I was like, what?
Walter, what's up, bud?
It's the guy that like this like math came to him in a dream on there. You know what I'm talking about? Like a god.
You're talking about the Indian mathematician like Ramanujan or something. I can't pronounce his last name.
I think
or his name.
I think we're talking about the same guy. Came to him like a dream, and it's like the most advanced form of math to this day.
What he was doing doing combinatorics, and he has struggled with the Western notion of like proof. Like you have to justify like the formula that you've come up to do this kind of counting. And he struggled to do that. Most of his explanations were like it just kind of came to me. But it's not like the most advanced mathematics, as there's no real structure to what he did. But he was quite effective in coming up with these combinatorial formulas, these ways, clever ways of counting
So he just
situations.
he didn't know what he was doing, but he did it.
Well, he had no formal mathematics education, so he was in a way self-taught. Yeah. But eventually, was discovered, and when a mathematician, Thomas Hardy, brought him over to Oxford, and he studied with him there, and they did some rather important work together. But I think butted heads a little bit because of
Are you talking about like Sir Vasa Ranujman?
Yes, that's who I'm talking about.
I saw him yesterday.
All right. So the point of what we're looking at is this creates a new model for us. So we can say A equals P e to the RT, where again, P is that initial amount. E is that number that we just talked about. R is your rate of change as a decimal. And T is our time unit. So we can answer questions involving systems where really we're expecting the change to be happening at every instant. So let's say that we have a certain bacteria population that under ideal conditions will increase by 94% every hour. And let's say we have initially 100 bacterium. I should say just bacteria. We might ask, how many bacteria will we have in like 6.5 hours? So this is a biological system, right? In fact, this population of bacteria should be kind of changing at every instant because the bacteria aren't going to reproduce like uniformly all at the same time. And a certain time, it's going to be kind of whenever they get around to it. Everybody kind of agree with that? That there'll be some variation there. So we're going to use our the initial amount is 100. The rate of change is 94. And it's 0.94 every hour. So I can just plug in 6.5 as it's currently written. And then I can just go to my calculator. So you should notice on your calculator, on the left-hand side of your calculator, there's the letters LN on one button. Above that button, though, in blue, is a little e to the power x. That is the button that we're going to be using. So I'm going to do 100 times. Then I'm going to press second and the LN button. Then I'll do 0.94 times 6.5. So in 6.5 hours, I now have 45,034 bacteria. Whoa. It's a lot of goobers that we have all of a sudden here. So if we have a biological system where the rate should be kind of where the system is kind of changing at every instant, we should be using this model. But we might also want to use this model in like a financial or compound interest situation. Suppose that we have that we've invested, $6,000 in a account that pays 4.5% annual interest, compounded continuously. What is the account's value in 5 years? Again, the key word here in separating this compound interest situation from the previous ones is that we notice that it's compounded continuously. It's not yearly or monthly or hourly, it's continuously. That means like at every instant. So again, we're going to be using this new model. Even though this is a compound interest situation, the fact that it's changing continuously is the part that tells me I want to be using this model as opposed to the compound interest model we had talked about before. So 6,000 times e to the 0.05 times 5. So $7,513.94. Is that okay with you guys? So those are kind of the two situations that you'll run into that we want to use this model for. Or two situations. Anyways, there's lots of situations kind of in natural sciences, where things are changing continuously, like this. How many of you guys have talked about radioactive decay in either your chemistry or earth science class? No?
I've heard of it, but I don't know what it is. Like, I remember doing it, but I don't know what it is.
Well, that's a natural phenomenon that is something that can be described using exponential growth or decay, and would be something that's a change that's occurring continuously, right? At every instant, some radiation would be emitted from your substance. What radioactive decay is, you take a an element that has a certain atomic weight to it, or atomic mass, I should say, and it will lose some of that mass by giving off radiation. That radiation can be in the form of, or it could be in several different forms, and the resulting element would be a little bit lighter than the one you had before. So sometimes you end up with a wholly new element, sometimes you just end up with an isotope of the same element that's a little bit lighter, depending on what kind of radiation is going on. But that radiation is kind of, if you talk about any measurable amount of material, you're talking about just hundreds and millions of billions of atoms, right? If you have anything that's a tenth of a gram, think about how many millions of atoms that is, right? So the radioactive decay is happening for each of those atoms kind of continuously, because there's so many of them. One of them's doing something at any given time. So again, that's a situation. Or you can talk about electrical capacitance is another situation that is a physical phenomenon that would be changing kind of continuously. So what a capacitor is a short-term way to kind of store electrical energy. So if you have a circuit with a capacitor on it, all the electricity kind of goes along the wire in your circuit, gets the capacitor, kind of builds up in the capacitor, and then after some amount of time, it'll start releasing the energy to go back, continue along the wire. It's not like a battery per se, where it's kind of long-term storage. This is a short-term storage, but it's a way to change the voltage or the amount of current going through a wire. But the way that energy kind of is built up and released in a capacitor is also something that can be modeled that way, in which the change is kind of occurring continuously. So the last thing I want to talk about today is graphing with exponential functions involving E. So our general form in this case is just things that look like this. And here, that coefficient on the x is all that we need to determine whether we're growth or, I'm sorry, I should say that. Now it turns out that every exponential function that can be written in this form can be written in, or transformed to be written in this form. We're not going to worry about how we'd actually do that in this course. That's beyond the scope of this course. But it could be. But to actually graph one of these things, nothing really changes for us. So let's say we want to graph y equals 2 times e to the 1.5x minus 3. My a is 2, my b is 1.5, and my k is negative 3. So since the a is positive and the b is positive, I know we're talking about exponential growth. I know that my horizontal asymptote is always y equals k. And to make my xy table here, I have no h in my general form, right? Now, when I had h, I did h minus 2. Since I have no h, I'm just going to do minus 2, minus 1, 0, 1, 2. And I'll use those numbers every time when I don't have an h, like this. Everybody okay with that? To get the y coordinates then, I'm just going to go and plug these into my formula. And I'm going to get some kooky numbers whenever I do this, just FYI. But that's okay. That's just, when we graph with e, that's what we're going to get. So negative 2.9-ish. And then negative 2.6-ish. Oops. Negative 1. I should probably start writing this down. Oops. Last one in here. That's about 6-ish. And then 37-ish. I'm only going to graph up to 6 because 37 is just too big to be practical to graph in this situation with everything else going on. And that's okay. When you're graphing these ones with E in there, it's a little bit harder to make sure you don't get some, or don't get a kooky number like that in there, but that's okay. We'll just ignore it. I have enough to get a good picture, right? And then domain and range still going to work the same way. The domain is still all real numbers because it's exponential. And the range is still going to just depend on a and k. Here, since the a was positive, I know we're going from k up to positive infinity. that's the gist of it here today, folks.